detect motion or change or some event like fire or spark or something in the frames. That is what you want to do. So the frames are fed into this LLN after the extraction by CNNs, and then that features will go into LNN, sorry, LSTMs and RNNs. Sorry, I'm mispronouncing both these things. So it's RNNs and LSTMs. LSTM will come later. So feed that into an RNN, and then you can find the sequence data. You can find the sequence in which events have happened. So there was an explosion. So did it start as a spark, and then did it become a fire, and then that fire when then ignited some explosive thing in the warehouse, and did that explosion happen like that, or was it a sudden explosion without any kind of preload? Then that's probably a terrorist activity, right? So this is how a security cam evaluates these kind of situations. Okay, mostly this is kind of post-mortem analysis after the event has happened, but it can also be used for early warning. Okay, so why sequences matter? Precisely that matter. Okay, we want to do early warning in most cases. We know a lot of things follow sequences. We know a lot of things are time dependent. They are chronological. They are in order. They have a certain repeating seasonality to it. Okay, so all these data sets are like that: speech, text, DNA, stock data. So now the biggest AI revolution that has happened is this. What is it? LLMs, right? So language models, huge language models, billions of parameters, a few thousands of billions of parameters rather. And how does it learn? It's basically learning the sequence. It's the same way we remember things. When you forget, probably you know some old bhajan or maybe some devotional song, and suddenly you forgot, and then if you go back to a point where you remember, come back from there again, sing the song, and then in that sequence you might be able to find out what you forgot. Something might click on. That is the sequence property. So the thing that came prior to what we want actually decided this. They had a correlation. This kind of correlation is called the time series correlation or autocorrelation. Correlation onto the sequence itself. That means the yth term is correlated with the y minus y n minus y minus first term, y minus second term, y minus third term, etc. So the terms which came before it, they decide to some extent the next term. Okay, so we expect stock data also to be like that, so that we can predict the market and then make a lot of money out of it by betting the right way. But sometimes the bets go wrong because markets are very volatile, and your predictions may not hold up. So let's see what was the traditional approaches to this kind of sequence learning. So traditionally, we had bag of words, n-grams, Markov models. These are all very powerful models. Even now, they are being used. Okay, before LLMs came or deep learning in general came, POS tagging. It's one of my areas. My PhD is in mathematical linguistics. So computational linguistics basically was a core subject that I had a lot of interest in, and this basically had this problem such as parts of speech tagging. That means you give a sentence, it will look at the sentence sequences and then tag each word with its parts of speech, like noun, verb, adjective. That was done using n-grams. Then we had context identification, basically what it was saying, how it was saying it. Okay, that was called bag of words. So frequency, based on frequency, TF-IDF. Remember the Google's PageRank algorithm is also based on, PageRank is different actually, but TF-IDF is basically their search, okay, of relevance. How do you find something is more relevant in one document than the other? Based on the frequency count of the word. So the search keywords and the words associated with the search keys like synonyms, antonyms, etc. They have this is relationship is very strong. So these things are more associated with the other words. So basically looking at associations in that way, we call it bag of words. Basically the association comes from the time dependency, co-location or correlation. Okay, you can have two things. Either they are co-located or they might be correlated. Correlation means semantically they might mean the same. So people would use them as interchangeable terms. Like going at speed and going fast, speed and fast, they are correlated. Okay, they are like synonyms. Co-located means speeding car. Car is related to speeding. It's very counterintuitive, but most of the embeddings are made like this. So India and Pakistan, they are co-located because whether we like it or not, that is how Americans term them. Every time Trump says India, Pakistan, people are getting irritated. Indians at least are getting irritated because of that, because saying India, Pakistan the same breath. So, but that doesn't mean anything. But that is how language is. So this is co-located. So I was expecting India and Pakistan to have completely different embeddings, but they happen to be having almost the same embedding. Embedding of India dot producted with the embedding of Pakistan will give you something like 0. Okay, that means they're almost in the same spot. Okay, so that much of bag of words. So an engrams, Markov models. Markov models, yet another model, sequence learner. Probably in casinos, to predict what is the most likely number that will come, whether he's using a loaded die or a fair die. That kind of things can be found out using Markov model. By looking at the numbers the dice are throwing. You don't know which die he's using, but you can actually write down the numbers that are being shown on the top of the die. So if a fair die, all numbers will have equal probabilities. If it's a loaded die, some of the numbers have more chance than the other number. So if he throws the die enough number of times, this can be figured out. So a sequence of numbers can be transformed into a sequence of say F for fair and L for loaded. L, LF, something like that. So we don't know what is this rule of shifting the dice. We don't know what sort of loading that other die has, but we can actually predict it. This is called hidden Markov model. Okay, we use this a lot. It's hidden Markov models. Speech processing, hidden Markov model. Even now, the major workable things apart from the deep learned speech models, nowadays a lot of deep speech models are there, but still there are a lot of legacy models in English and Arabic which still uses hidden Markov model. Okay, HMM, very useful algorithms even now. Okay, then what are the limitation? Now that is where the limitation comes. This is also limitation with not just RNNs in general. Most of the sequence learners have this limitation. Long range dependencies. That means if the sequence you are trying to learn, the pattern is very long. Okay, like instead of 26 alphabets, let's say we had like 1,000 alphabets. It need not be 1,000, just 150 alphabets. So if I'm looking for a sequence learner that always predicts the next alphabet in the sequence, having 150 alphabets, unique alphabets, gets me into trouble because that is a very long sequence to learn. Anything more than 50 is a long sequence to learn. Why do I say 50? Because that is the experience. This is from experience I'm telling you, not just mine. Generally what you see on the papers and published works, you can also check. Okay. Anything more than 50 is you usually considered crossing the border, danger zone of long-term dependencies. That means your model will not function properly. It might give you wrong predictions. Okay, it cannot understand. Sequence is too long for it to remember. That is the main reason. Why it cannot remember? We'll come to that in a short while. Okay, and this is one of the main reasons why RNNs needs replacement. It needs a different algorithm replaced because it cannot deal with long-term dependencies, long-range dependencies. Curse of dimensionality, because sequences are very long and they're very unique. Very high dimensional cases might emerge. You don't know where to limit. Okay, so this dependency can be very long. Even for normal time series models, we call it something like lags. Okay, and there are multi-dimensional dependencies. There can be dependencies at different frequencies. Okay, there might be daily dependency on the daily thing. There might be a weekly dependency. There might be a monthly dependency. There might be an annual dependency, or even 6 months dependency, like a seasonality of the climate. In airlines, that is a big problem for us. Every time we try to predict traffic, it goes out of the window because every 6 months, because of climate, there will be a performance problem in most of the flights in India because Delhi climate keeps changing. Delhi is the hub for Air India. So Air India, Delhi climate keeps changing. and during winter we have left and right and center flight cancellations and flight delays because of the frost. So this is a big issue for us. So this kind of large sequences increases dimensionality, increases number of parameters, very difficult to train them. That is a fact. Even for the new algorithms that have somehow learned to remember long dependencies, still cursive dimensionality is a reality. We'll come to that again. Neural networks before sequences always feed forward. CNN is an example of that. It's feed forward. It always feeds forward, right? There is no each neuron did not require any feedback from its own output. But sequence learners do have a feedback. That complicates things a little bit. So we call this as temporal loop or temporal time-based back. The mic was on. Okay. So this temporal looping is what we call as feedback. So feedback is a very unique aspect of sequence learning networks, including RNNs. Okay. So we'll see how the feedback is made. So the after, before, during information needs to be passed into this. Otherwise, that pattern will not be complete. Most of the information is in that ordering of the data. So that order information is very critical. In all our previous examples, including CNN and all that, locality might be there, but ordering was not. But it was order invariant rather. Most of the other machine learning algorithms do not have any issue with order. We cross-validate. We shuffle the data up and we cross-validate, and still it will give you the same result. So order is not significant there. But in sequence learning and time series data, it is extremely important. Okay. So how RNNs came to be? So it was first propounded by Jordan and Ellman in 1980s. Very useful architecture. So recurrent connections is basically the feed-forward connection, feedback connections. We call it as the hidden state. Okay, even multi-layer perceptrons can have hidden state or projection states, but the hidden state in RNN is crucial. You can't have an RNN without this hidden state. So every RNN layer intrinsically has a hidden state, which is called the feedback state. Okay, so it's a hidden state. The output goes into the input. Whatever input you're giving, that goes into the hidden state as second level input, and then the output of the hidden state goes back into the hidden state along with the input that we are giving, as well as it goes forward. After some time, it has to move forward. Okay, so how many loops does it take for the hidden state to figure out that it is like this? So this is the same dilemma that we have with combinatorial and sequential circuits, right? So combinatorial circuits are very easy because there is no feedback connections. But sequential circuit, like a flip-flop, the moment you come to sequential circuits, timers, flip-flops, whatever, memory elements are all sequential. They have this problem, right? Same issue. RNNs have the same issue. So since RNNs are algorithmic and not circuits, they're not realized in hardware. So we don't have to worry about clock pulses and clock edges and all. At least that much we can be happy about. But still, that issue is there. Now, I want you to visualize a backpropagation that happens through time. So that is called BPGT, that backpropagation through time. What is backpropagation through time? Now, usually backpropagation happens from the input into the output layer. Whereas in a RNN, there are two backpropagation. There is a normal input to output backpropagation happening, but in between that, there is also the the instant level backpropagation. We call it instant level. That means, let's say time t equal to 0. T equal to 0, the hidden state had output, some output, ht. Now ht has to be fed into the t equal to 1 instance of the same network at the same layer as ht. So ht will go into ht plus 1. ht plus 1. So this is basically coming out of your screen. Okay, so the earlier network that I showed you, so imagine this. So this is a complete network. X, H to O. X is the input, O is the output, H is the hidden state with the feedback loop. As you can see, the feedback weight is W. Basically, it is the same connection. So it is taking its output and putting it back into the same input. and the weight for that is W, which is a matrix. Okay. Now, how does this work? Now, I want you to imagine this network. This is not going forward. Basically, forward passes from X to O, that is upward. Okay, you have an upward and a sideward motion. So you're basically looking this from a kind of a drone visualization. You know, the drone is flying on top of your head. If you have a neural network on a page, the drone is above the page. The page is three-dimensional, so that it can not only see the forward pass, it can see the lateral pass also. So this is called the lateral passing. So basically, that loop creates this kind of a back propagation through time effects. Okay, so during this back propagation through time, the weights, none of the weights, I mean U, W, or V, are changing. The only thing that changes is the output HT. Okay, so it starts with HT, then HT minus 1 goes input into, sorry, okay, this is T is in the middle. This is T minus 2, T minus 1, then T, and T plus 1, and then finally T plus 2. Okay, so maybe it is stopping at T plus 2. How do you decide how to stop? Because that is the length of the input sequence. If your input is T plus 2, the sequence is N, then there will be N instances of this back propagation happening. Okay, so instance wise back propagation. Each instance is one instance in time. Okay, the same network duplicated. So the first instance is T0, then T1, T2, T3, etc. So it is that instance. This is the forward pass. This is the normal forward pass of any neural network. Okay, and this is the lateral pass. Lateral pass is only for recurrent neural networks or any network where there is a feedback connection like this. See, output of H at time T0 is not consumed at the pass at T0. It is consumed at T1. And then that output is considered at T2. Then the next output is considered at T3. This is the best way to understand back propagation through time. So the H alone, to train the weight W itself, it takes all the sequence to, sequences of length, say 10, then at least 10 times this H, starting with 0, going all the way till H9 will be generated. And then that H9, including H9, will be fed into the output 9. And then the output sequence is generated after that. Okay. So this mechanism of having the output in this fashion is what we term as back propagation through time. Okay. Now there is a catch. What is the catch? That is what we are going to see. Challenges. That is called vanishing and exploding gradient. Now, probably you've heard of these terms. So anyway, since this is a class, I'll have to detail what this problem is. So we'll understand this in detail. What are the applications? So these are the applications. I already said speech recognition and language modeling. That core applications of this technology. So are the current language models using RNNs? Of course they are, but they're not called RNNs. We call them as transformers. Okay. So understand, transformers is an update, is a super update of RNNs. Okay. And they are recurrent in nature. Transformers are recurrent networks. This is one of the reasons, even if you don't remember or retrain the network, if you don't remember the previous output state, LLMs, all the commercially available LLMs say that no, the LLMs don't remember anything from your previous output. Okay, the prompt, everything, it just takes the prompt, generates an output and then forgets everything. Then for the next instance, it is a clean slate. You can again prompt. ChatGPT doesn't work. ChatGPT has a memory, so LLMs actually remember everything that you've done before. But if you are using an LLM through a program, then you know that every OpenAI call, if you're using OpenAI, doesn't actually have any preload. It doesn't have any memory. It's completely stateless. That is what they say. But I don't believe so, because the moment the LLM, it's one instance, that instance is not being killed, or that instance is not rebooted from the trained models all the time. Instance is running forever. It's just that it doesn't remember any input and output. So every time a new prompt comes, it will just eat it up. But I give a prompt, probably a bit of a long prompt. It actually had to work a lot on that prompt. It's a huge prompt, complex task. And then it gave me an output. Immediately, you're sending your prompt. there might be a conflict, because even though they don't explicitly remember anything, these transformers are basically sequence learners. They can remember some portion of your past, because they do have what we call as a input gate and a forget gate. Forget gate might not always be open, so it might not be always open to forgetting what the previous prompt actually gave. It is in volatile memory. It is within its volatile memory. It's very, very volatile. It will not stay for long, but your prompt will get affected by the previous prompt that was given, the previous work that LLM performed. This has been proven 1,000 times in my experience. Unexplainable, of course. This is the only explanation we can come with. And finally, when I confronted the LLM architect at Microsoft, he had to, somehow agree to it. There was no way. Everyone knows this. It's a known secret that LLMs do have retention memory. Okay, so even if they're completely stateless, there is something called retention memory that actually retains a lot of stuff that. So because of that, Air India basically asks for a dedicated LLM. I mean, the instance that we are using is completely dedicated to Air India only. Everyone inside Air India will share that instance, but all the instances that we want. So we don't use OpenAI directly. We use Azure OpenAI through Azure Microsoft, cloud, SecNet. It's like a on-premises cloud, so it's completely closed, and nothing goes out of Azure. Okay, so all the data is clean. This is one way to do it, but LLMs do remember stuff that you. So if you give a lot of data, personal data, it will remember, and next time someone asks to synthesize some data, it might accidentally synthesize your data. Okay, that kind of thing is very famous. It has happened. It will happen. Not very, very secure in that way. They can't help it. That is simply the way the machine works. Okay, that being said, let's proceed. So these are the challenges. And then finally, the solutions. Yes. So if not RNNs, what else? We have LSTMs, 1997. Gates. Okay, he's the guy who invented LSTM. So cell state overcoming vanishing gradient. So it found a way to remember the cell state, replacing the hidden loop back with what is called as the forget gate, input gate, and the output gate. So basically a gated network. These gates themselves are neural networks. That is the main catch. The gates themselves are neural networks. They also learn what to take in, what to throw out, what to accept, what to read, etc. So they learn that in combination. So that is one of the reasons why LSTM stake is one of the worst trainable networks. It takes a lot of training effort. LSTMs don't train easy. They train very hard. They have to be trained hard. Otherwise, these parameters don't get set. So imagine you have a layer of LSTMs. LSTM layer is not composed of neurons. They're composed of LSTM cells. And every cell has at least 4 different small neural networks attached to it. This is the complexity of LSTM. Okay. So the next architecture is, GRUs. GRUs are gated recurrent units. Okay. They're simpler gated architectures. They train much faster. They came in 2014. Now they are getting much more popular. Most of the things that LSTM used to solve, now GRUs can solve in a much more simpler and faster way. Things which require a lot of model retraining kind of aspect, where trendy data and all. GRUs are better. For example, stock data. LSTMs are not good. LSTMs take a long time to train, and I myself have proved that LSTMs are not very good. Our RNNs actually are better for short-term predictions. The best is windowed CNN, but you should know how to window. You should the window size and window slide are actually hyperparameters that should come from a domain expert. But we got better results with windowed CNN. Bidirectional RNNs, that is another thing. So, but this again has that kind of a issue. It's not completely free of the vanishing gradient thing. But what happens is it can compensate. The moment the gradients start vanishing in one direction, you can train it from the other direction with the reverse sequence if you know the sequence already, and then it can compensate for the loss gradient. That is how it is. But very long sequences, it doesn't survive. Then deep RNNs. These are stacking layers. So to some extent, this again only complicates the training. There are some cases where people have found this very useful, but specifically, this is only going to complicate things even more, because you're training RNNs themselves have the issue. Deep RNNs are going to have more issue. Okay, because more than one RNN, more complication of a complex system. Okay, so regularization again dropout, that the same dropout that we discussed in CNNs, same thing. It just turns off certain nodes randomly, stops them from getting updated. So only the remaining will undergo stochastic gradient descent and update the weights. The remaining are stopped. Okay, so that stopping is actually chosen randomly. Not the same thing is not stopped all the time. Then they never get trained, right? So randomly, like 50%, 25%, or 75% is stopped. Only the remaining gets trained, and then the batch continues. So convergence will be very fast if you do this. Optimization, same Adam, gradient clipping, Adam, and there are some other popular ones that also you can use. I'm not able to recall most of these optimizing stuff. If you look at the API, it's much easier. RNN variants, clockwork RNN, ind RNN, so many other variants are there. That also you can look up. These are things which you can do some hands-on and find out about these variants. Key applications, machine translation, yes, of course. Speech to text, same thing. It's instead of machine language to language, it's just language to text, signal to text, basically. Sentiment analysis, of course, again the same thing. But we don't use RNNs for any of these anymore because of LLMs. LLMs are getting cheaper. We used to, even when LLMs were there, people used to. Personally, I used to do that. We used to have recurrent networks that will predict sentiments and all that kind of stuff from embeddings. But why we had to do that? Because it reduces a lot of LLM cost. Precisely around I would say 20 to 30 lakhs per month of cost it was able to save. So now the LLM cost has gone down, so they don't mind using LLMs for everything. And this is actually performant because it's a local model that can perform better, specifically trained on certain type of sentiment. They can perform. Local models always perform better. LLMs, the performance is not performance in the sense the time it takes. The output is unquestionable, very, very high accurate output you'll get. But the time it takes for the call to go to the LLM and the result to be fetched back is kind of frustrating. Sometimes the calls are very, very time consuming because too many people are using it. So, that kind of things will happen. So local model will help boost performance too and save costs. So we still use this for some of our use cases where performance is paramount. Okay. So beyond RNNs, CNNs for sequences, as I said, something called WaveNet. Basically, it's a windowed CNN approach, which is called a wave. But we didn't use this for our paper. This came much later. Our paper was written in 2017. Seek to seek is another approach. It's an encoder decoder kind of framework, which again helps. So this seek to seek is a precursor to the attention and the transformers that we know quite well now. Okay. So yeah, then came attention mechanism. That is in 2015. Attention is all you need. There's a paper like that. So please do read that paper. Attention is all you need, which is a paper for transformers. So soft alignment of sequence tasks. That is what attentions do. It's much better than just hard sequence learning. It can actually learn patterns of repeats. Basically, it can learn long distance seasonality. So neural machine translation is it was a big thing even around like 2018, 19. Lot of papers, lot of people doing thesis on this. Basically, they use RNN plus attention. That is what they usually do. But then transformers came and then they simply, the term to use is stone rolled it, okay, flat. So that it's 100 times better. So everyone shifted to that. Sorry, random finger touch. I'm trying to point to that and then accidentally I will double click. Okay, so limitations of RNN. It's based on seek to seek. Actually, it's not the seek to seek. It's based on this is wrong. That's not what it means. It's based on sequence length. That is what it means. Limitations of RNN clearly is based on the length of the sequence. That means the sequence is too long, it will not work. Parallelization issues are there. That means scale up, you, because it's dependent. It has sequence has this kind of dependency that normal data doesn't have, right? Because if my sequence is a vector, you need to wait for that entire vector to arrive, and you can't process anything before that. The entire data has to be provided in the same order. No parallel activity will happen. You can't parallelly process data. You can't do a map reduce on time series or sequence data. Same reason. RNNs are time series and sequence data, so you can't do a map reduce on it. Map reduce will parallelize data rows. Here there is dependency between rows. My next row depends on my previous row, so I cannot do that kind of parallelism. Okay, that is a parallelization issue. Sorry, I'm really sorry about this. Very, very clumsy hands. Step towards transformers. Yes, of course, it's a step towards transformers. So that was the last point. I'm sorry. So we've been mentioning that all throughout. Then modern deep sequence models, of course, transformers in 2017. Attention is all you need. Please read that paper. Very, very useful. I mean, the way they've put it, you can understand attention. I mean, it might, some places they've used a lot of math and all, but basically you'll get the idea. Then you can watch some simplification videos are there, which basically simplifies what attention is all about, pictorially. And all. It's very easy to understand what attention means. It means you can actually understand things from a context within the sequence. Okay, that is all is necessary. So I saw a video recently, and he was giving a good example. Example is, I want to buy apples and oranges. Apple is going to release the new phone, so there is an ambiguity between apples. So on what context does the machine understand what apple actually means? So I want to buy apple and orange. If I say that, then orange is the attention there. Orange is a fruit. So when I club, so this is called a co-location again, right? Co-location has a very powerful meaning. So that attention using this co-location to disambiguate apple. So this orange will pull the embedding of apple towards orange, and then apple becomes the fruit. And then it is disambiguated. Whereas when phones occur on the other sentence, you definitely know we are referring to the company, a technological company called Apple, okay, which manufactures iPhones. So this is the idea. So that is called attention. This is the idea of attention. Self-attention explained. Basically, we have key query value. This is basically the way in which the attention happens. So key is the apple here. Query is basically the attention. Query is not that, just that. It is the context basically. And then finally, the value is the embedding to which the key is associated with. Okay. So I mean, very vague kind of explanation. The way I understood, this is how I remember this. So it's easy for me to decode to everyone else. That is called self-attention. Okay. This can disambiguate a lot of things within single sequences. Hence the term self-attention. Okay. So that simplified and revolutionized the way we saw languages. So without any haste, without any complexity, the idea is you can stack up transformers in billions. We saw that. I told you stacking up RNNs was a bad idea. Of course, it was because of the limitation. Once the limitation is off, then there is nothing stopping you from doing this. But then in between, we had another emerging thing, which is called hallucination. Nowadays, the LSTMs are so good. After GPT-5, I'm using GPT-5 day in and day out. It's amazing. A lot of things earlier has been completely resolved. Hallucination is almost to less than 0.00001%. It gives you exactly what you ask. It doesn't hallucinate that much. I mean, at least it's almost like talking to a super intelligent human being who doesn't hallucinate. Scaling up. This is an old, I took this from an old slide. So basically you find old stuff here, GPT, Llama, T5 and all is T5. Not even in classrooms we recommend T5 as a small text model. Okay, uh, it's kind of obsolete. You can use T5 as like a frog for dissecting and understanding how LLMs work. BERT is, on the other hand, is more useful for the embeddings. BERT embeddings are still used a lot now. It's more useful. And GPT and Llama has transcended time now. GPT-5 is there's nothing like the original GPT. And Llama, after Llama 4, Scout, Maverick, I think there's a bigger version. I don't know what it is called. Maverick and Scout, I'm aware of. They're out of this world. Basically, a great challenge to GPT-4. But now GPT-5, we have to sit and see what Llama 5 is going to do. Okay. Llama is equally good, sometimes even better than GPT some places, but GPT, I always felt GPT is better. Reasoning thing, I think Llama is scoring better now. RNNs today, still used in some niche real-time flows. Why? That is the catch. The real-time and low resource tasks. Why? Low resource and real-time tasks, because it is a fast algorithm. It doesn't have the complexity of LSTM and all these, what came beyond RNNs, things that they're all complex, and they solve the problem by adding complexity. So that cannot be used in a real-time setting, because it takes a long time to process, long time to compute, long time to feed forward. RNNs do that very, very easily. And if the sequence is small enough, why not? Why do you want to go for extra computations? RNNs are able to do it. Use RNNs. Don't use LSTM. Don't use fancy stuff. Okay, so always go with what works. That is the philosophy in data science all the time. It has been time-tested thing. You don't need to do super duper things just for the cost that you have to use it. Maybe only in academics we do that, because I've done that a lot in academics. Simply make, just for sake of writing a paper, we overhype things and do. But once I moved into corporate, I found that the basic of the basic models is sufficient to produce a very good result, and that is all they look for. Maybe later, when the input gets complex and complicated, we can go for the complex algorithm. Okay, future directions, hybrid models, efficient. This is actually an old slide I told you. So we are already past this part. Okay, efficient transformers, state space models. State space models are all over. It's all transformers now. Okay, now the actual RNN. This is how I looked. I showed you this earlier. Now let's see how the basic problem with vanishing gradient is. It's easier to explain this using this picture. Now we have the eigenvalue equation. If you don't remember it, I'll just decode it for you. So you have a matrix called W. So this W matrix, when you multiply it with a vector V, will be equal to some lambda into V. If V is not the eigen vector, it will give you some V star. So if V is the eigenvector, then the equation will have V on either side. But if you don't have V, you might have a different vector. That means WV by lambda is some V I plus 1. So let's look up that V in sequence. Okay. So basically, in your hidden layer here, your W is not changing between back propagations. Otherwise, every time you do back propagation, you have an update coming and then you back propagate with the update, right? But here the update is not that. It is the same old W matrix that you use to actually find your gradient all the way. So every back propagation, every time you have to back propagate, is W here, W here, W here, W here. What happens is, if you keep on multiplying a vector with the same matrix, so basically gradient is, you would multiply W with this V, you get a V1. Let's say W into V0 is V1. And then you take W into V1, you get V2. Okay. And the gradient is V1 minus V0. That is your gradient. That is the error that you use to update the weights later. Okay. But you don't update it, in between that, the back propagation through time. That is the specialty of this time-based backpropagation. You don't update W at all. You wait until the whole sequence is backpropagated across that whole instance. The whole length of the sequence length is 50. You'll have to do this 50 times. That is the n here. So W into n times V, eventually what it gives you is some V star. And then with V star again you multiply W. If you multiply W enough times with the vector, eventually that vector will become its eigenvector. That means it is saturate. you'll get a point where W into Vi is equal to Vi. Okay, it will not give you a different Vi plus 1. So what will be the gradient Vi minus Vi? The gradient is 0. The gradient simply vanished. This actually comes from Markov chains. Markov chain says that if you keep on multiplying a matrix with a vector, eventually there will be a point of saturation. That means some A into X, then A squared into X, A cube into X, there is some N beyond which you will keep getting the same X dash. A10 into X will be X dash. A11 into X, that means A to the power 11. A is a matrix raised to 11. A multiplied 11 times with itself. It's a square matrix. Okay, we agree. Because it's a feedback loop. So same input, same output. So it's definitely a square. So you can take a power to it, right? So if you take it n times, it is going to not be helpful. So you're going to get the same thing back. At some point within this back propagation in time, this gradient is going to die. Why? Because now to explain it in terms of eigenvalues, if Wn, so the same effect that W creates on Vi, the eigenvalue can also create. And what if the eigenvalue is less than 1? Most of the matrices are normalized weight matrices, and its eigenvalue will be less than 1. And what happens if you keep multiplying with a fraction to a vector? Eventually that vector is going to become 0, right? That is vanishing gradient. But if the eigenvalues, see, the only case this works is when the eigenvalue is exactly 1. But you can't be sure of that. None of the RNNs can have eigenvalue exactly. You can't set a W in such a way that you have to engineer this W for lambda I, that is the at least one eigenvalue to be equal to 1. Then this will work. You can backpropagate indefinitely. You can learn very, very long sequences. But this will never happen in your data. Your data should also agree. Okay. So W, the moment you start updating W, its eigenvalue will start changing. So then if eigenvalue is greater than 1, then we have the opposite. We have what is called, you see, the example is given here. Let W be this matrix. So this matrix, eventually you raise that to 50, you raise W to 50, what happens? The error is 9 into 10 raised to minus 16. Fermi gradients. Eventually this is going to go out of the precision of your computer and your gradient is going to become 0. Same thing with exploding gradient. It's going to go out of your memory and you will not be able to backpropagate. So if eigenvalue is greater than 1, it's going to magnify exploding and vanishing gradient. This is the problem. So this is the easiest way to understand vanishing gradient and exploding gradient. It's using the eigenvalue concept of the weight matrix W, because we are simply going to multiply W many times. Don't keep multiplying any vector with the same matrix. Eventually the gradient, the differences between the vectors will die and you'll start getting one saturated vector after some n times multiplication. If you multiply that vector n times with W after some n, which is very around, let's say around 50. That is why they are taken 50. I told you 50 is the limit. Any sequence greater than 50 is considered to be long. Actually, even 50 is itself long. You can see that the error is very, very small here. Okay, so this is the concept of exploding and vanishing gradient. Now coming to how we can remember long sequences. Welcome to LSTM cell. So LSTM cell diagram we'll see first. This is easier to know. So this is how an LSTM cell looks like. So there is this hidden state. HT is the actual output. HT minus 1 is the hidden output from the previous instance of the cell. Okay. But there is no weight here. There is no weight multiplication. So you see this cross thing. It is basically element-wise multiplication. That is all is happening. There's no weight. Okay. So all this is element-wise multiplication. So what is CT, FT, OT? OT is the output gate. FT is the forget gate. So plus is basically element-wise addition. If you put an into, this element-wise multiplication. Okay, so that is what is happening. XT is the actual input data. And we say I generated this in ChatGPT 5, of course. But again, it's not foolproof. The X connector and all is wrong. But this is the basic cell. You can also search Google. I wanted an original image, so I don't want to copy from Google, even though I've copied other images from Google. So I was just trying out. So I didn't notice it when I was copying it. I did it in a haste. So this is the basic thing. You can search for the LSTM cell structure in Google and do some learning yourself. So these are the gates. Basically, these gates are also neural network themselves. Their vectors, input and output vectors are there. So basically, it's one layer, one or two layer perceptron networks, which gets trained along with the entire thing. Okay, so it is this cell that is stacked up in the layer. So a layer of like 20 or 30 LSTM neurons basically means the 30 LSTM cells like this. So you have to train all the gates of each of these cells. So it's not traditionally the weight problem. So this helps. There is no weight multiplication or that kind of backpropagation. Backpropagation becomes very straightforward because we are not doing any gradient descent of that nature. The expression just became linear. Okay, that is what happened. So again, input states is just explaining what previous hidden state and previous cell state. CT is a cell state, HT is the hidden state, XT is the input, FT is the forget gate, and OT is the output gate. Actually, there is also an input gate, which I think is not there. So what is input gate? Selective memory writer. So it writes what it needs to remember from the previous input and the input of the hidden layer, previous hidden layer. It will write as output into the HT. So input gate is used as a selective memory writer, and the output gate is a selective memory reader. What is the forget gate? It helps erase, it masks certain inputs. So it is a selective memory eraser. So what things should be erased? Basically, it is learning. It is like learning the filter coefficients that we learned, that discussed earlier. Basically, the mask. Okay. So you have your input vector. Out of this input vector, what I should remember, what I should not. Basically, it's creating a mask pattern, and it basically does a dot product, not dot product, element wise multiplication. Dot product also adds adding. So the output here is a vector, but the vector will have masks in it, like an element wise AND operation is being done. That is how the gates actually help. So that those are the weights that are getting trained basically. So what should be the thing that it will get trained as when the training process is there? Okay. Okay. So yeah, so I think that brings us to the end of the slide. Now let's move on to the code. So I think a share would have gone. Yeah. So I'm going to move on to the code. Yeah. So this is a basic spell checker that I've created. It uses, I think it uses TensorFlow and Keras. Not very good, but I'll show you the output. So I've shared this code with you. So here, how it is done is basically it has got a list of words. It's training on these words. It's training on these patterns. Okay, and we are trying to generalize all the patterns to all the spell checks. So basically, it learns. Okay, when there is a T, it is usually followed by an E when the T comes in the third position, something like that. That kind of rules is what is expected to learn. But LSTMs don't make a very good RNNs. Neither RNNs make a very good spell learners, because this is something which is done using basic automators. They make tries and basically the spell checks in your mobile phone and all, which works very well. They are working on some tries or um, some sort of automator based code algorithms. They are actually pretty good, because literally hard coding all the whole dictionary into it, and then that data support is a stateful system where there is a data support. You don't need to learn, you don't need a machine learning system to actually do it. But given the scale, if you give the full dictionary and enough number of epochs and enough complexity to the RNN, like multi-layer RNN or multi-layer LSTM, this is going to be more successful. At least I think you can get 80% accuracy out of this. Now it is pretty lousy. You're not even getting any accuracy. Loss is 2.29. This is like 200% loss. It's very bad. So you can actually see out of the examples given, top 5 characters, autocomplete for APPL was Apple was good. That was one good thing. Then for banana did not come. Band actually came. I don't know whether that was part of the training. Maybe not. Then India should have come, but nothing came. Indeed could have come. It did not come. All nonsensical stuff came. Gravity, grave, GRAVE. That was the easiest one, but it never gave that because it is coming close, but not up to the mark. That's because of the data is too huge. You have to train with a very large dictionary pool, and you have to train for a lot of epochs. So just to save on the time and this thing, I just want to show you a concept of how this is done. So this is basically using Keras. I'll try to make the window big because the model build is actually important to us. So here is where the model is being built. You can see the symbol RNN. So it's using the Keras inbuilt layers. Sorry, I think it is using an LSTM. I actually asked for an RNN, but I think this code actually gave an LSTM here. Okay, so yeah, this part is generated. So this is how this is working. It's okay. LSTM RNN idea is the same. Basically, it is to apply it in some realistic context. You can see the activation is relu. So this kind of thing you can actually observe. You can generate more code, and you can actually look into GitHub and learn. These are all standard things. How you build the model, how the architecture is made. They're all very standard. So we don't have to go into details of even hands-on is not needed for this. Okay, it's just you can basically this is the kind of stuff that we cut copy paste in every code. It's very very straightforward, very simple, just stacking up layers one on top of the other, and you have to see the shape because if the input is of that shape, that should be the first layer. Okay, and the shape should be 128, which should come from the input. So input layer, that is why we put this input layer. Sorry, 128 is the size of the neuron. We don't say the input layer, but we pass that input. Okay, input, where does the input layer gets the data from? Gets from the data. Okay, the size of the data is found from there, the size and shape, of course. Optimizer is Adam, and it is going, you can see. So the model fits, training is done, epochs. These are the hyperparameters. So every deep learning code always has these hyperparameters. Batch size. So one thing I'll tell you to understand how this batch size works. The training is happening in stochastic. The algorithm is stochastic gradient descent. Why stochastic? Why not normal gradient? Why not steepest gradient descent? Now, usually deep learning is very data hungry, right? We don't use deep learning unless we have enough and more data. Don't use deep learning when you have very little data and you try deep learning and doesn't give you any accuracy. A basic regression fit would have worked better, like only 30 data points. If I do a simple linear regression, it would have worked exceptionally well. Deep learning cannot give you accuracy with just 30 points, and it is an overkill to do deep learning on that kind of thing. Data is also very straightforward, not many features like 5 features, 10 features, no problem. Just do a normal machine learning, and it still gives you very good accuracy. But what is batch size? Deep learning works with a lot of large data. So in order to train, it has to actually iterate over all these data, and that too for multiple epochs. Not once, it moves to the data multiple times to train the weights, right? So there is a trick. The trick is it will batch the data. That means it will randomly find batches of 64 data points. And it will randomly select one batch at a time for every epoch, maybe a few batches. So from every batch, it will pick one data item and perform backpropagation using that. The remaining 63 items are discarded for that particular instance. This is enough. This is enough. You don't need to actually exhaustively move through all the data. Increase the epochs if you want to. Convergence is guaranteed. This is why we call it stochastic gradient. There is a randomness to it. It randomly picks one data element out of the whole thing, right? So all deep learning algorithms work like this. That is why it is crucial that we set the batch size not too small, If you set it too small, the training will go forever. I mean, the time increases. If you set it too big, your accuracy might not converge for the given number of epochs. You might have to increase the number of epochs. So this is a trade-off, and this is something you do with trial and error. You can set it. Okay, there are also standard grid search methods to do this, but since deep learning training is not something you can repeat indefinitely, I don't recommend grid search on it, especially when you're using CNNs. Each training run will take 30 minutes. If you do a grid search with 75 values of batch size and 100 values of epoch size, it's going to take 75 cross 100, 7,500 times. It's going to do 7,500 into 30 minutes. Calculate that yourself. It's going to get real crazy. Nobody wants that amount of time being spent, not to mention the computation and cost of computation that you're wasting. So that is why we don't do it. So especially we just keep it at some point. Eventually it will work. So 64 batch sizes recommended for medium size data. If the data is too big, then you can look at 128 or maybe 256. And usually we choose batch sizes as just the same way we choose kernel sizes in CNN as squares of powers of 2. It's just a convention, nothing big, but it feels good, when you have these things as a power of 2. Okay. Validation split, you already know, it's for the cross validation. 15% of data is kept aside for every epoch, and it uses that random 15% to do validation. Basically, test. It doesn't use that for training that epoch. It just tests using that 15%. You can go through this code. So I'm going to minimize this. Output is here. I showed you the output already. This uses Keras. Okay, so this is basically using the Keras library. Now the other example, I think this is slightly better. I'm not. You can be a better judge. So I just created a small data to create some. So I think it is reading data from some source. Is it just randomly creating data? Probably yes. So there is a kind of function. So this becomes more predictable. So that is why it is able to predict well. This code doesn't have much significance. I'll just, because this code basically, not that, the one below it. So that actually went under this thing because I used a different size for the text. Yeah, create this one. So yeah, here I'm creating some dummy data. So you can see how the this thing is. It's creating some dummy data, writing that into a file. Yeah, so basically it's kind of random picked. So don't expect any accuracy for this. And here we are running it. So this will run. I've already run it. It might take some time to train. Kind of. Maybe I can just put it aside here. No. Are you able to see this this window?
Yes.
I'm sorry. Close it. Can you still see?
I mean, not the window, only the code that we can see.
Okay, fine. But there was a window over that chat. I mean, that meeting minimized. This thing will come now. So I was trying to move that. I couldn't see the code myself. Sorry, this is not the one. Okay, this is the one. Sorry, wrong. I went to the wrong window. Okay. So you can see that it is trying to train, and yeah, it's only 9% because it's random data, so it's giving you loss of 0.8. That means 8% wrong validation. Loss basically it's calculating. So accuracy is fairly good, not bad. It's only calculating loss because it's random data. So I didn't put accuracy as a. So probably the accuracy is around 90%. Okay. Yeah, you can see the graph. So not very accurate, but since it is random data, you can't expect more than this. At some points, it is actually catching up. Maybe here, it's catching up. So this is how the prediction goes. This is an LSTM prediction. This is the actual random stock data. since it is random, don't expect a good prediction. But anyway, it is trying to predict. But I have a better example here from LSTM. So this LSTM is from scratch, just like the CNN from scratch that we did. I also have a vanishing gradient example. So basically, this is an RNN. It also prints the vanishing gradient. You can see how the gradient is moving. WX, WH. So you can see the bias and the gradients value here. In the first step, this is the gradients before the first iteration, and when the loop starts, it actually starts decreasing. So it's only doing 30 iterations now. So even after 30 iterations, it is almost gone. There is no gradient. There is no error to backpropagate and make your model more accurate to learn from. That is the gradient, vanishing gradient. And this is basically the LSTM from scratch. Now this will be interesting. So this is one piece of code that you can actually go. I tried to comment it as much as possible. This is an old piece of code. This is not new. Um, I tried to compensate. Yes, forward pass and all was already there. I think the application was common. Yeah, the application I generated and I pasted it here. So the application is basically it's trying to figure out the sequence of alphabets. This is something it can do very well. Okay. So here you see it is trying to learn the sequence A B C B. So it's always A B C A B C A B C. Okay. It always goes A B C A B C A B C. And here it is stopping at A B. So final sample, it is able to generate ABC, ABC. Here it went wrong. It generated, no, it is correct. ABC, 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 AB, C, A. So it actually added AB, that B. It stopped with B, right? It's able to predict A. So this is pretty good. And this is complete LSTM from scratch. The cell and all, everything is created. You can take a look how it is done. Gate pre-activations, you can see. So this gives you some idea on how the mechanism of LSTM works. And gated recurrent units is actually an improvement over LSTM, which is much more efficient. So that is something you can, try and, kind of a DIY example. Okay, so I think with this, we can come to a close. So I've shared both these files with you, the RSTN from scratch and the CNN from scratch files. I think enough examples are there. Is there any other example you would personally would want to see? Maybe I can make and send it to you. So I'll just stop sharing this. Yeah, I think, yeah. Yeah, there's a doubt from for creating the model for identifying fake voices. Okay. For creating a model for identifying fake, this is from Aishwarya Sudeep. Fake voices, NN, or which combination of NNs are preferable? Let me try to answer this. Model for identifying fake voices. That means something like that. That is the idea, right? So, yes, sir. Yeah, okay, okay. These are preferable. This is
Sir, is it okay to we use a LSTM with RNN or CNN for that?
Vijay, your video I think is stuck. Is there any network issue at your side, or I think better you can turn your video off and try to talk. It looks like there has been a technical issue at the side of Dr. Vijay.
No, he will
Oh,
be connecting again. He told he will be
okay,
connecting
okay,
again.
okay,
Some net
okay,
issue is there.
okay.
Yeah, sorry about that. I think my connection was severed. Can you hear me now?
Yes, yes.
Yeah. So regarding your question, I suggest that you look into some speech models rather than making a deep learning model to from scratch. It might be better to. There are already deep speech models, so that is what I think you should do. Building a speech model from scratch is not a good idea because it takes a long. These there are some pre-trained speech models which can identify this kind of thing, and bot voices are just as good as human voices. I don't know how feasible that might be. Maybe from the kind of tone, what you need is prosody and I mean these are basically speech parameters, right? Epoch and prosody. So by looking at these two things, I think you should be able to classify bot and non-bot human voices. But I've heard better. The bot that AI is planning to launch for its call centers, you will not even understand it is not human. It is that good. It is that good, exceptionally good. It sounds not just sounds human. It basically it is like human. The tone, tenor, you can even hear the typing voices. That actually I think they've added artificially for the feel of the call center. But it is 100% a call center, I guarantee you. And um, it's very very acute. I mean, everything you say, your number, everything, and it reads back the PNR code and all. Oh my god, amazing bot. So I'm not fully it might be feasible. I'm not judging, but it will be a very difficult problem. That is my call on that. The classify bot voices, and because they're not no longer very different. Bots are able to speak with the same tone and tenor of human beings. Maybe the old bot voices you can maybe I don't know what ChatGPT's new version. You can try, but I suggest the deep speech networks which are pre-trained rather than training our own.
Okay, sir.
Oh,
Thank you.
I have a problem. I lost all that questions. If you have posted a question, you can please post the question again. Yeah, welcome, Aishwarya ma'am. So, if anybody has posted any question, I lost all that when my connection severed. Bad Google Meet is very bad. This is the only call app that actually does this. Everywhere else, it will have the same chat content. It never goes away.
There have been a few more questions. I think I can actually copy and paste all of them in the chat window now.
Please do, sir. Please do, sir. I will try and answer all the questions. Yeah, one PPT I think I haven't put. That also I'll add to that drive. After the class, I'll add that.
Oh yeah, that was the only thing extra, right? I mean, there was something like kindly
Ah,
share the RNN PPT. I
I,
think,
I,
yeah.
I remember reading that.
Yeah, that's, yeah, yeah. Okay,
We'll
okay,
put
okay,
that,
okay.
sir.
That's what I
Yeah,
think.
yeah.
Yeah. Nothing
Okay.
more. Yeah, I have a question. Like, how do we actually calculate the number of hidden layers that is required in a neural network? Is there any criterion for that?
Usually, it depends on the problem. See, problems that need more resolution of data. Suppose, see, if I'm this is a question that hidden layer question is very prominent when you are making autoencoders. Autoencoders basically encoder decoder architecture. So you don't know how many hidden layers, how many step down or step up hidden layers you want for that particular transformation to work. Encode decode kind of transformation. We use autoencoders a lot for anomaly detection because this what we call as ideas you are able to encode the data in one side, and then there is an opposite operations like Um, there is a matrix, you can multiply your x with w, and then there is a w transpose, w dash, that actually gets you back the x from the output of xw. Xw is y w transpose, w dash transpose is basically your x. Okay, so I can actually measure the distance between x and x dash and find how much error is there. Okay, now this is a typical example where I need to compress the data. So basically, it is denoising the data for encoding and then blowing it up later. Um, so we usually step down. So the idea is that if you step down at a particular pace. If you have like 32 neurons in the beginning, we just go by a count of 16 and then 8, and then again go to 16 and then back to 32. So this is how you decide based on the problem and based on your experience. Then actually you're just trying it out. These are hyperparameters that nobody can calculate. Eventually it will work. See, it doesn't matter whether you choose 200 epochs or 200 neurons or 300 neurons or only 50 neurons. It doesn't matter. Okay. It will eventually work. Only the accuracy might be the convergence speed, the speed by which the network trains might get affected if the correct optimum hidden layer is not provided. But otherwise, that doesn't have any importance as such, because eventually you will get the trained network will train maybe 1 or 2% of accuracy, plus or minus 2% accurate. That's it, but it still work. If the data is wrong, data is random and doesn't have a pattern, then no machine learning can work, right? So this is basically a hyperparameter. So it's not, we can't also do this grid search on deep learning because it takes so much time for it to train. So basically we just go by a hunch. We just follow this pattern of step up and step down, like you do step up transformer and step down transformer. We do the same thing here in the hidden layers. So if you feel that you need resolution, for example, if it is a network, text network, that basically are giving embeddings into the network, and you want to find sentiment. So this is a problem where you need more resolution. So if I put more resolution, I feel that the network can filter information better. So my hidden layer will have more neurons than the input layer. So I'm just stepping up the resolution. Step down is done when you expect a lot of noise. So usually for CNNs, naturally it's a step down. So CNNs basically, what they're doing essentially is they're throwing away noise. They're churning the information. They're also doing transformation, making that information more accessible to the so the feature is getting churned. The feature, idea of feature itself is to make the information in the data more accessible, more observable. Information is hidden inside data. So you convert it into features, you do feature extraction, you make it more accessible. That is exactly what CNNs are also doing. By removing noise is one way to do it, one way to see it. So there it is definitely step down. And there are some conventions that we follow, like the kernel size is always a power of 2, like 8, we do 4, 8. 4 is very small, so most of the realistic images, it will be like around 8 or 16, depending on the requirement, whether you want more data, you need to churn more out, or you need to filter more out. You make the filter smaller when you need to filter more things out. You make the filter bigger when you need to get more resolution. So that is like stepping up in CNN. So it's basically a hunch, and most of the things that we do, we follow. We basically look up a common network that was put into some common problem. Like if I want to do scene classification, what I want to do is a scene is given to me. I want to classify it as forest, coastline. This is a very popular thing. Like CIFAR dataset actually does this kind of scene classification, right? That is one of the initial use cases of CNN. ImageNet was actually made for this kind of thing. But if you want to use the same network for something else, what I'll do is I'll not make a network from scratch. Either I'll transfer learn. I'll use the same scene classification. I'll use the feature extraction portion of the net, which is already trained on this huge data set. I don't have to retrain it. Only the last portion, the dense classifier, because this time I'm not going to classify it as forest and coastline and So I just want to do a bi-classification like so. My problem is a subset of that original problem. I just want to see whether it's a water, if there is water in that place or no water. So that is all I'm trying to do. But the same network will try to figure that out. This, when I was working in Amrita, um, they had a remote sensing MTech remote sensing course. They used to do this kind of tasks. So that is how I learned about this hyperspectral image. Their core is of basically image processing and basically satellite and remote sensing kind of images. So this coastline detection, water detection, all that was part of their projects. So I used to guide projects for them, and they used to do all these kind of things, and it used to come out very well. They never went to actually a point where you retrain any kind of image network. All feature extraction started with VGG60. We just took the feature extraction part of the network, pre-trained, and we just put it to transfer learn, add the dense network, classifying softmax layer, that alone you add, which is a dense layer that you add to the end, and that alone is reused. So that is very easy and it works like a charm. So as far as possible, we don't need to decide on these kind of things. Nowadays, nobody does it. Even image processing, people, they just reuse most of these common. It has become so off the shelf that there's so many networks. You just have to, Google and find the right network, download it, and for that purpose, you can just repurpose it to your job by, just by adding a dense layer and doing a basic training on that. That's it. We were able to generate OCRs for 12 languages by just doing the same thing. No retraining of the segmentation layer or the text identification layer, which is all the CNN core CNN layers, all part of VGG16. Only and the remaining segmentation, the text segmentation is done by Segnet. That also we didn't have to touch. Only the last dense layer where the character is identified to be this particular class, that part we had to retrain, and effectively we were able to use it. We use Keras OCR. The name is Keras OCR, but it's a separate JIT project by some guy. It is a free tool, so we can reuse the code if it is not for commercial purposes. We are a non-commercial organization, so we can reuse any code. I mean, we don't sell software. So this is my idea. These are all hyperparameters. It's very difficult to put them, say that this is the amount you will use. This is how you have to decide. We just go by the convention of the step up and step down as, twice or maybe 1/3, a 30% increase. Likewise, you can decide what that step up accuracy. If it is too deep, then you don't need to do huge step ups and step downs. You need to do small step ups. You can make the network more deeper. More deep the network is, the better will be the feature extraction. So that is also true with this embedding, text embedding networks. Every time you try to do topic identification using some classifier and all, or sentiment identification using classifiers, I told you that we want to bypass LLMs and its cost because we made some local models using basic LSTM, CNN and all. But it works on the embeddings are actually taken by using Hugging Face models. That is also local. So that is also easy. And then for that, we use the step up, step down. So initially we did with lesser number of less number of hidden layers. The moment we increase the number of hidden layers and the scale, we scaled up the step up by 30%, step down by 30%. The accuracy started improving. So it does have effect. I'm not saying it doesn't, because initially the lady who, my colleague who actually tried that out, she did not have any idea how this is done. And Hugging Face was giving like 700 dimensional embeddings. So it's quite dense. And you need a lot of depth for that information to be extracted. So that kind of understanding you get with a lot of experience. This is my take on it. There is no hard and fast rule of how these hyperparameters need to be chosen. There's nothing. Just follow what we say. So initially we started with that follow thing. We used to look at papers, take stuff from there. Mostly it is transfer learning, so we don't have to make a decision. If at all we have to make a decision, create a network from scratch, we do that in this by using these things and what other people have done before us. We just follow, we just copy that architecture from them, and then just slightly tweak it here and there. Maybe you will get some accuracy, some improvement on what they already had.
Yeah.
So
Thank you, Doctor. Yeah.
thank you, sir. So
Yeah. Thank you,
just
Doctor.
to finalize,
Yes.
I promised that I will show that you can just Google my name. You can go to my, most of my papers are there in my research guide too. So papers that actually deal with these kind of things might be interesting, right? So what I suggest is that that can be, you can just take a look. I don't publish a lot nowadays because now I'm just I'm just a company employee. I'm no longer a academic. I can't call myself a current academic, even though I do a lot of academic work. Still, it's very hard because I don't publish that much. Maybe one paper in a year, but I do make a point that it is published in some good journal. Just out of curiosity, I'm doing it. R&D doesn't like doing a lot of such kind of jobs, which is wastage for the company, you know. But they're not very hard and fast about that too. They gave me permission for this, so usually they also give permission for that kind of activities. But usually we focus on patents. So I'm just trying to access my Scholar. It is very slow. Just share that window to show you some papers that might be interesting. So here, basically, um, this paper obviously is both LSTM and CNN. I told you this is a sliding window model. It got a lot of citations, almost a pioneering work in that area of stock prediction using deep learning. So we were able to very effectively show that LSTMs don't work that much. It's very bad, especially forecasting is very poor in LSTM. It is able to do one step, but long, even maybe 1 or 2 days forecast, it is going wrong because it's learning a lot of unwanted history. It's not able to forget all that because that forget pattern is not something that the STM can pick. But when you give the fixed CNN window, that history is being cut off, so it has more recency. It's able to learn better. So there are also other type of this NSE stock market. This is again using deep learning, using CNN and LSTM and RNN kind of. They have also used GRUs for this. Just go through the paper and you'll find this. This is also an interesting work. This visualization for malware classification. This looks at the execution file, the bytecodes of malware. Microsoft once published these bytecodes for some hackathon or something. So we were able to get those bytecodes. We immediately made this paper, and this accuracy was astounding. Every malware family it is able to recognize very accurately. Unbelievable accuracy it was. But we cross-validated and still it was coming 100% accuracy for one family. We also tested this package, to see what application is being used in the outgoing package. We used Wireshark to capture the packages, and that was fed into a network, CNN and MLP. That also was very interesting. So if you go through this, a lot of things will be there, mostly using deep learning. Everything is not deep learning. There are a lot of other things too. Yeah, so thanks a lot. I think that should conclude what I have to show you today. I think I have lived up to the expectation. Everything I told you, I delivered, I hope. So you are the final judge. Thanks for the opportunity anyway. Big thanks to Uni sir for calling me. And it's a big pleasure, as I said. It's an honor to do this kind of a FTP session.
Yeah. Thank you, Dr. Vijay, for once again delivering an excellent session in our FDP. And you started by introducing the time series data and then introduced the recurrent neural network. and then you move to LSTM, GRU, bidirectional LSTM, bidirectional RNN, and a deep RNNs, and then you explain the problems of exploding and vanishing gradients. And finally, you showed an implementation using LSTM, and that was in fact a great session for us. And once again, thank you for offering to take a session, offering to take, in fact, two sessions, one in CNN and the other in RNN in the FDP. And from the side of the Department of Computer Science and Engineering, Rajiv Gandhi Institute of Technology, Kottayam, I would like to express our sincere thanks, and we would like to have you as a resource person in our future FDPs also. Thank you.
Yes, sir. Thank you.
Thank you very much, Vijay. Thank you. Thank you.
Thank you, Nizar.
And dear participants, we will have sessions on large language models tomorrow. And please be here at 6 p.m. itself. Thank you. Have a good night.